for me, it's a very good pleasure to have Alvaro Hacar here as our guest and to have this seminar from him. We already invited him a couple of years ago. Actually, it was 3 years ago during the COVID lockdown, and he gave a nice presentation, but it was in remote. And now, finally, you are visiting in presence. So welcome to Rome, and it's very pleasure here. So Alvaro is a well-known personality in the study of the star formation, in particular the ISM. He did his PhD with Mario Tafaglia in 2000. He started in 2011 and did his PhD in 2013. But he associated his name mostly to one topic that at that time, we're talking about 10 years ago, was very, very relevant and is still open, an important open question right now. And it was at that time, we had the Hacar that was flying, and the Hacar Space Telescope started to give us a snapshot of the structure of the ISM, the interstellar medium. And we started noticing that all the clouds in the ISM has this beautiful filamentary structure. And in that time, Alvaro was doing his PhD, and he started studying those filaments and associated his name to a very good result that I think is still under discussion somehow, but it's actually we are realizing that how those filaments are. So the question that Alvaro was working on was the structure of those filaments, the inner structure. And I think he was sure he will present us. He associated his whole research field to study this bundle of fibers that compose the molecular clouds. And the time has passed after his PhD with these nice results, and he moved first to Allegro, work as a scientist. He worked first as a postdoc in Vienna, then he moved to Allegro, work as an associate scientist there in the Almark node in Holland, and then finally he got his permanent position in Vienna as associate professor, linked to the fact that he won an RC project to study actually the structure of this filament. We invited him here to give us a review of the nice progress that were done from the initial analysis that were done 10 years ago, but much more has been learned from that. So his seminar is about this topic, and so the floor is yours, Alvaro. And even if I ask people to make their question at the end of the talk, I know that there will be some interaction, but people, please, people from online, if they can write their own question on the chat. So the floor is yours, Alvaro.
Thank you, Eugenio. Thank you for everybody for being here. I mean, Eugenio almost spoiled half of my talk, so you already know. No, but I realized that, I mean, it's obviously much better to be here with you in Rome. I enjoy the city, I enjoy the place. I realized that I have 3 challenges when I was preparing this talk. One is one that Eugenio already mentioned, that I was giving a talk in 2020 with, I went back to the image, almost kind of similar title. So I hope either you forgot about it or you are new here, so I can surprise you. Second one is that, I mean, I want to bring new concepts. Some of them are mentioned, but some of them are older. And so I hope I can still surprise you after all. And and I hope that, I mean, new ideas, particularly in front of this audience, can be discussed. And this is why I'm asking everybody to make your questions whenever you want. So why we are, at least myself and some of the people here in the room, discussing these things is because we want to address one of the most fundamental questions for star formation, which is the origin of what we call the initial mass function, the distribution of masses of the stars when they are born. As you know, from the field stars, we know that stars follow a mass distribution of this IMF, which is basically dominated by low mass stars, so the solar-like stars similar to our sun, at least in number, and a long tail of what we call high mass stars, stars more massive than our sun. This correlation is a fundamental piece that we need to for the understanding of the baryonic matter in the universe, is because it determines basically the entire energetics that we know. So we know that the mass is dominated by low mass objects. We have many of those. And then all the radiation, all the feedback processes are dominated by these more massive stars. So understanding why we exactly have this mass distribution is one of the key, and I mean, many angles and people doing from local to stratigraphic studies are trying to do. The interesting thing is that when you look into textbooks to understand how these low and high mass stars are formed, you typically find two different models. So one is the model for low mass star formation, so stars that are isolated and then form in quiescent environments, and they do it slowly, and they evolve and form that way. And if you look at how high mass stars should be formed, they typically form in really harsh environments, really active environments, dynamic environments, where the stars are formed really, really fast in large groups, in clusters, and then they interact with each other. So the question, and one of the questions that have always been there, is that are they actually these two modes disconnected? They are two different things. And if so, why then always end up into this initial mass function? If they are disconnected, they should not be, right? So can we find a connection or not between these things? Some of the progress was made in the last 20 years. I mean, as Eugenio said, one of the peaks was when I was doing my PhD, and came from the study of both the local molecular clouds, and here we have the experts on the galactic scales studies, but we found that star formation is closely related to the formation and evolution of filaments. Here you have an example. So a molecular cloud, like in this case, a torus, a low mass cloud, contains really long filaments of gas that then have these dense cores inside and then fragment and form low mass stars. This structure basically is a key piece of information that we learn thanks to Herschel and thanks to other things. We know kind of this from, I mean, almost 100 years ago, but the big progress was made due to Herschel. With this, we came up, the community came up with what we call, a more structured theory of star formation, and I will show you a simplified model of what it is. Of course, all of this is backed up by models and equations and stuff, but let me show you what we think about low mass star formation. So when you look at a nearby molecular cloud, this is the Aquila star forming region observed by Herschel. You see that the gas inside this cloud is heavy structure in these filaments. So you see these column density regions that are not just blobs, but they are elongated stuff. And inside them is where you find these YSOs. So the giant stellar objects, they always form in these filaments. So what we think now is that low mass stars, at least, they form in a fragmentation process. You form a filament that fragments and form what we call cores, so like these spheres of gas that eventually collapse by their own gravity, and they form low mass stars. We have a really nice analytic theory for that. That's a beautiful thing, that if you combine the stability of one of these objects, something that has to be cannot be collapsing really fast because otherwise this doesn't work, but if you kind of manage to keep it due to turbulence, due to pressure, due to magnetic fields, the way you like, you can induce perturbation, you fragment them, and then you form your cores that are solar-like. So the typical core of, that will end up into a solar mass star. The problem of this model is that at the same time that explains the low mass star formation, basically prohibits the formation of high mass stars. And this is because in order to have this process to happen, your filament cannot exceed a certain mass, what we call the critical mass per unit length. The reason is that if you are more massive than that, then you will collapse radially and you will not fragment. You will basically collapse into a spin. And then you have a maximum on the order of 20 solar masses per parsec available to form your stars. And this becomes a number that I will ask you to remember for later. Then you introduce perturbation, you fragment on scales of 0.1 parsec, and then that gives you your low mass core. But at the same time, it gives you an upper limit on what cores you can form in there by this pure fragmentation. Because of that, when this is the other mode of star formation, the formation of high mass stars, require different things, and people came with different models, what they call the turbulent core or the competitive accretion model, so different ideas on how you could accumulate enough mass at the beginning, so later you trigger the formation of high mass stars. And the problem of these models is that, well, it worked in theory, they work in the equations, but when we were looking for these precursors, I would not say there are none, but there are very, very few of them that we can detect. And I mean, Alessio is probably an expert on these things, but I would argue that these are not the true conditions of high mass star formation, or at least it's not the most obvious ones that we can see, and people look for them a lot. So meaning, a lot of observational time spent trying to find these things, and maybe we have a handful of them, but for the entire galaxy, I mean, this is not enough. So what ALMA shown us is that high mass stars form in also filamentary environments, but a special type of them. And we call them hub filament systems. So these are filaments that are not like isolated, but they are connected, forming junctions. And this is one of the most considered examples by Nicola Peretto. So you have two, I think one of them is 80 solar mass star, or prospect of 80 solar mass star, and it's at the center of this junction of filaments. And this is something really important, and I will also ask you to remember other things like these regions are, these junctions are low aspect ratio regions, so regions that are filamentary, but globally are kind of spherical. They have high column densities, and they are connected to large accretion rates. This is the way you have and you put the mass together to form your high mass star. So there is a connection with the filaments, but not exactly the same as the one that we saw for low mass stars. So maybe there's still these two nodes. Let's see. I don't think this image needs a presentation in this audience. I mean, you might know the PI of this. But something that we have learned, particularly with these large-scale surveys, is that this process is basically the dominant process of star formation in our galaxy. And I mean, most likely in any galaxy, just the way the ISM likes to structure in these filaments, and then you have these high mass happening regions when you have these amazing networks of filaments. So the questions that I would like to discuss with you today are three in particular, and again, please feel free to ask other things. But first of all, one key question is how do actually filaments form and fragment, so fragment and form stars inside them, particularly when you look at these ginormous filaments. So these are things that exceed a lot these theoretical expectations that we have for filament fragmentation. In this case, then, how you generate a specific condition for high mass star formation and the other ones, I mean, how do you differentiate them? And in particular, again, are actually these two modes do exist? And if so, how they could coexist to form, in the end, this IMF? So these are the three like top-level questions that we can discuss today. So again, Eugenio spoiled my results, but I want to still mention a couple of things. Perfectly fine. How we end up in some of the ideas that we are developing in my ERC. So during my thesis, I was looking at one of these Herschel filaments, the typical Herschel filament that you can see, and in this case, resolved in nearby molecular clouds. So this is called the Barnard 2013 filament in torus. This is a really famous filament since Barnard, so 100 years ago. And Herschel, the Goodwell survey, used this as a prototype for star formation. So because you have a really well-defined filament, at least at these scales, and then you have several stars formed in there. So ideal fragmentation is there. There's one single problem of this interpretation, is that the mass per unit length of this entire guy is 50 solar masses per parsec. I told you a few minutes ago that you cannot exceed the 20 solar masses per parsec because you will collapse. So this object is physically impossible, at least in this interpretation. It will collapse if there will be a pure 50 solar masses filament. It will collapse radially faster than any fragmentation mode that you can impose in there. So you will not form stars, and still you do. So how this is happening? Well, I'm a radio astronomer. I'm working with molecular lines, and we observe the central region, the type thing that I'm showing you, the central region, in molecular lines, in CO, so a tracer of the diffuse gas, and N2H+, which is a tracer of the dense star-forming material. Something really funny that we saw is that, well, there are some positions where you have clearly one velocity component. That's great. You have one structure on the sky there, and this diffuse and dense at the same time. So you have this density structure inside there. But there are regions where you see two velocity components. So two kinematically separated structures along the line of sight. Sometimes you have two, sometimes you have, and they can move, they change in intensity, move in velocity. You have sometimes two, sometimes three, sometimes four. And you have regions where you have 5 velocity components superposed along the line of sight, meaning that you have several structures superposed in your line of sight. What we did, and that was my thesis, just to reconstruct this velocity field and try to identify the structure in them. And we found something interesting. Now, going back to the Herschel image, this is the Spire 250 image of this region. Here you see the cores being formed, so fragmentation in this case. And this is what they call a filament. But if you look carefully, this is not just one single axis structure, right? So there is, even in Herschel, you see these wispy structures, so forks that break this thing in many, many pieces, right? So something that looks really simple in continuum, or apparently simple in continuum, when you do this kinematic analysis, you can demonstrate there's actually a collection of small-scale fibers. What Eugenio said, we call them fibers, you call them small filaments if you want, doesn't matter the name. The thing is that within one large-scale structure seen by Herschel, there are many small-scale structures that are kinematically separated and also physically. And you see this thing that forks here, and basically several of these structures that are already twisted. So we call them fibers because it looks like a fiber in a rope. So they're like things that are twisted and forming a large-scale structure. But it's basically the substructure of one of these objects. Why is this important? Well, it's because this is what you need to form your low mass stars. These things are much smaller than the large-scale structure, that there are pieces inside them, but they are transonic structures, so you don't have turbulence anymore inside them that disrupt them. They are coherent, they are continuous in velocity, so they are single structures. And then they have this close to critical mass per unit length. Then they have the conditions to fragment and form stars. And actually, some of them they do. So when you look at one of them, this is the most active one, this is one of these fibers, then you fragment regularly, and then you form your low mass stars. So at least in this simplified case, you need this fragmentation, you need these fibers, but call them filaments inside filaments, to be able to form your low mass stars. So this is what we learned. But of course, we are not here to talk about low mass stars. This is boring. We are talking about high mass stars. So how does it change in the case of a high mass star forming region? And for that, the nearest example that we have is the Orion Nebula cluster. So this is the OMC1 region inside here. So this is a region forming the transition stars, so several high mass stars together. And this is part of a really long, I hope you see this in this projector, a really long filament called the integral set filament in Orion. So this is a several thousand solar masses filament, 8 parsec long filament here, and at the center you are forming a massive cluster. Problem again, here you have 350 up to 500 solar masses per parsec. So more than 10 times the expected mass per unit length that you can have for pure fragmentation. So this object, again, should not exist. How does it happen? Well, then let's see what ALMA tells us. Before showing you what ALMA shows, I would like to show you what we knew about this object before that. So this is the N2H+ map at low resolution of this filament. So here the cluster, the Orion Nebula cluster is here. You have the trapezium star, the Orion Bianca star, and this is the filament seen at low resolution. So this is like 20 years ago. You're looking at this filament 20 years ago. And then you see, okay, you have the filament, you have the clumps. So that's it. We solve it. This is our fragmentation scale. And because we are in a high mass star forming region, when you look at one of these clumps, then you measure the width of one of your lines, and these are turbulent lines. So we go back to our models of turbulent high mass star formation. Okay, 20 years ago, then we move to resolutions similar to Herschel. And look at what happens. So from these blobs to something that your blobs start taking shapes. And that's interesting. So just a small change in resolution changes your structure. So you see more well-defined things, and your blobs are now have hair. So they have different things that go in different directions. N2H+. So dense gas. The diffuse gas is even more complex. So the other interesting thing is that then when you look at your lines, this is, by the way, a line with an hyperfine. Forget about all these things, look at only this part. So we're looking initially like a really broad line, then you have two peaks. So your broad line break into narrower, still not subsonic, but narrower lines. So you still have turbulence, but things are not as clear anymore. So we are still 100 times less in resolution than ALMA. So when you observe this region with ALMA, you go from this picture to this picture. So your blobs are not anymore round this. Your blobs are not clumps. your blobs are basically a spaghetti structure. So breaks into tiny little things, like little filaments all over the place. So there is no single big blob anymore in this cloud. And this is thanks to the now superb ALMA resolution that we have. The interesting thing again is that your broad line that was supposed to be 2 then, now is there 3 really, really narrow components. So the dense gas in these high mass transforming regions is similar to the low mass ones. It's really quiescent, really subsonic, structuring this heavily structured actually in this case, and along the entire filament at a tiny, tiny little scale.
Alvaro, what was the spatial resolution here in natural scales?
4.5 arc seconds, so 2000 AU.
4.5
arc seconds.
So you use the ACA.
No, it's the ALMA compact configuration, the main array and the most compact configuration. So the nominal one is 3.5. We convolve it a bit to make our maps more sensitive and more stable. But yeah, it's the lowest ALMA resolution, and even then you already see this.
Those are not combined with single dish there. Those
It-
are only
No,
material.
these are combined with item centimeter offset. And I will mention it later. Without this combination, you cannot do this.
Exactly.
We have another talk later,
Yeah.
but I will show you some of these things. So, but okay, so again, your big blobs are not blobs anymore. They are basically spaghetti things. And of course, you can do the same type of analysis, and then you can, these are now over fibers over small scale filament, basically the same structure that we are seeing in low mass transformation, but at much, much smaller scales. Here you see 2 zoom-ins of these regions. Look at now the scale that we are looking at. So this is 0.1 parsec. These super ultra thin filaments are tiny, are in AU scales, 10,000, 15,000 AU scales in width. And they are all over the place. The structure nonetheless repeats itself. So when you have these quiescent regions elongated, close to equilibrium, then they fragment efficiently, with all these curves that you see here, the continuum sources and the wire source, and this is where you form your low mass stars. So at least in high mass star forming regions, the low mass stars are formed exactly in the same way, and then the low mass star forming clouds. So the process, at least, is not too much different at this level than the low mass one. The only difference is that it happens at really tiny scales, and this is why you need ALMA.
Can you remind me again what is this? The comparable scale in the torus fibers? Is it so one fiber in torus that you could resolve is larger than the fibers you see?
And several of them together, yes. So the width changes. If this is your question, I will not have the time. I can show you this later, but we have data to prove that the width changes clearly from that.
So the torus one are wider than the Orion ones.
By far, so
No, I mean the fiber.
the length also, yes.
No, the width of the single fiber, not the entire fiber. Yeah, that's the width.
That's a single fiber.
Oh, that's a single.
Yeah.
Okay.
Now this one.
Okay.
So 0.1 parsec. 0.1 parsec. Yeah, so if you are wondering about scales, so cores are no longer 0.1 parsec cores. If you want to see a core, this is a core. So
that one is called a low mass step.
yes, so the equivalent to the low.
The high mass.
Yes, exactly. That's the next question. So any other question about this, or can I continue?
Just a last comment, sorry. The evolutionary time of this white source here, the limiter source here, is the same in Taurus also in Taurus?
The evolutionary time, we don't know the evolutionary time of the YSL. We know the evolutionary time of the structures, and it's on the order of half a mega year. So we see class 0 and 1 stars associated to the fibers. We do not see class 2 stars associated to fibers. So these things recycle and change on scales of comparable to the class 0-1 time scales.
I have to rephrase my question before. If you go to the torus, the fibers start that you did was with iron.
Yes.
Okay. So the angular scale you could have said, I mean, the fibers are super resolved, let's say,
Mhm.
with respect, because you separated them kinematically, not because you separated them spatially.
Both. The region where we do both. So these are physically separated. I mean, these regions are overlapped.
But you didn't observe these with the similar spatial resolution that you did with Orion.
Fair point. So funny enough, we have a lower resolution, slightly lower resolution in Taurus than in Orion, just because we use ALMA and Orion are not here. This is resolved by at least I think 7 beams with not see substructure in there, but we are observing this region with the plateau de or not the plateau, Noema now, sorry, to do exactly this, to compare exactly the same thing. But we do not see further fragmentation even when we have many, many beams across with a single piece. So, I mean, it's definitely,
Come up with the
it's definitely something that we want to do. So.
There's also a study in sequence with the karma interferometer that showed that they are wider than the one with prime.
So the thing is that, and even if, and I will show you some comparable things later in, right? The width change. So there's a resolution issue in this case, but the width changes systematically. So, and I would like to invite, I'll send my student here who did the study on the width, so he can prove you that the width changes systematically. So the key question is what we just heard. Okay, but what about the high mass stars? I'm just telling you how high mass stars form. Sorry, how low mass stars form, not how high mass stars. The actual thing is that, I mean, this is a common thing. So the question is, can these networks of small scale filaments, don't call them small scale filaments, explain not only how the low mass stars form, but also how the high mass stars form? And that's the second part of my talk. And this is how we got this ERC project to actually prove and explore this idea. And we do it with something that we call emergence. And I will explain you what is later, but it's like something that perhaps you do not need a new physics, is that you need to consider these networks as a whole to understand the origin of high mass stars. So these are the things that we have here. So I invite you to go to our webpage to see different things, not only whether we see high mass stars or not, but we have all kind of technical developments on data combination. We will discuss this later. So things to archive, so to check the ALMA archive. And we have the first wave of papers coming out in these. Some of them are out, some of them are coming in the next few weeks. So what we did, one issue, as we just discussed, is resolution. So you need to have, at least to do this type of study, you need to have an homogeneous resolution, homogeneous data set. So the first step of our survey, of our project, was to say, well, we need an ALMA survey of many of these regions, low and high mass stars, homogeneously done. And then we observed 7 star forming regions, parts of the Orion A and B cloud, all with ALMA, all with the iron centimeter, all combined at the same way. And here you have the example, and we have, for instance, before we have the OMC1 region with the cluster, we have also the Flame Nebula, another high mass star forming region, OMC2, OMC3 for really famous regions of high and low or intermediate mass star formation, but also really low star forming regions like the 2023 and 1641 North. So we cover a wide range of conditions to explore these different properties. This is where you see it. I will not show it now. I mean, I can show it later, but it will be too much for it. So why we need this? Again, go back to the high set resolution. This is OMC3, one of our showcases. You see this big filament. You see the stars being formed along the filament, but this is not as easy as it looked like. I mean, when you observe at the single D resolution, yeah, you kind of see some substructure, but you're limited by resolution. This is what you see with a single D. This is what you see without. So resolution is crucial to understand the physics of these objects. And when you do that, look at this crazy substructure that we see here. That's even hard to quantify and explain, because I mean, this is just not just one or two things. It's like a spaghetti soup, a soup of spaghetti here that we are doing. And we need this combination, and we'll have another discussion at 2:30, right? Yeah. I will present the work from my PhD. Interestingly, we have many other tracers. Look at, I just want to show this as a beautiful example of what happens when you have this nice data. So look, this is the dense gas structure, so, and it's already complicated enough. This is the single disk of another molecule, HNC, so it's a trace of the more diffuse gas, and the complexity goes completely bananas here. So I have no idea how to describe this complexity at this point. So it's not only that you have this axis twisted and stuff, it's like, even the diffuse gas is full of I mean, I don't know, again, whiskers, if you want to call it like this, I don't know. I don't know, I have any idea what is that. We will explore this in the future, but the data are there already, well combined and ready to really go. My student Francesca also trying to do that. But
You have polarization data.
there are some regions that have polarization data, so OMSIF in particular has polarization from, and some of them, all the studies from Matthew, and I mean, these regions have been explored, but not all of them.
And you launch that they're filed with the
Right?
And then you launch that they're filed with the
Some are, some not. It's a complicated structure, but well, happy to discuss it. So, and this for 2026, when you invite me again to enjoy the pasta here. So what we did, and my other PhD student, Andrea, did a similar study. I will not spend much time because it's the same type of thing, but you can see that all these regions basically are a plethora of these tiny little filaments all together. We have now 152 of these objects. And so they are everywhere. This is the standard mode of fragmentation of the gas. The gas likes to form these type of tiny things. And then is when things get interesting, because now we have statistics, now we have multiple regions. Now we can do properties of these networks. That's the next thing. It's not about how individually they do, because I can also show you the statistics if you wanted. But basically, every single of these structures is identical in terms of coherence. So this is actually the way we identify them. You continue in velocity to find them. They are all sonic or transonic, so there is no much turbulence in them. And then when you look at the mass per unit length, this is the mass per unit length that you need to fragment and form stars. So, and that happens in every single region that we look. Not going to talk about this. We find the varying full half maximum as a function of the environment for all these things. Invite Andrea, and he will tell you. What I wanted to show you is the properties of the network, and it's how they not act individually, but how they act as a group. And something that we did, and I mean, something we explored in the past, but now we can do it much better because we have this homogeneous survey, is that, so if you measure the amount of dense gas that you have in your cloud, you get an area, you measure how much dense gas is traced by this N2S plus, and you count what is the surface density of your objects. How many of these objects you have in this area? How many of these fibers you have in this area?
Okay, so this is not the surface density of the fiber.
No,
It's the gas in the fibers. It's the surface density of the fiber as numbers of structures.
Number of structure per area. And we find this kind of linear correlation. I mean, it's of course not perfectly linear, and of course there are all kinds of biases here, but there's a connection between these regions, meaning that when you have more dense gas, you have more of these objects. The fragmentation is exactly the same, no matter whether you look at low or high mass star forming regions. The difference is that you have more dense gas available, and therefore you form more of these objects. These are the final Lego pieces that you need to build up these regions. These are probably a wrong analog in a sense that it's not that you build upwards, you build downwards. So you create a large scale structure and then this fragment really, really fast into these fibers, but it does it in some kind of regular way. When you have more dense gas, and this is the dense gas right now, so it changes over time the amount of dense gas. But then you form a constant rate of this.
The implication of this is that you basically form, even in high mass regions, first the low mass stars. Because you always get the
not necessarily. So we are not saying what forms first. We are saying what number you form. This is not telling you anything about the time scale when you form them. Telling you that the more mass you have, the more of this structure you form. But whether they form first or later is a different. And I will show you a bit of the evolution later, but this is, at least in this plot, you cannot tell that. Yeah, so we recover, you have to remember the number, but it's on the order of 95% of the mass that we detect in the dense gas, we recover it in this structure. So we are kind of completely, to call it like this.
the typical dimension in the lens for a structure to be a fiber? We consider a single fiber.
We do not,
have some minimum, maximum,
we do not, I mean, the minimum is the resolution of the instrument. We need to have at least, I think we impose like 2-3 beams or something like this. We do not have, we do not impose any conditions in terms of the length. We do not impose any conditions in terms of the width. We do not impose any conditions in terms of the aspect ratio distance. So we just follow what we call velocity coefficient, or something that if you can follow it, you will continue. Then stops. If it's long, it's long. If it's short, it's short. If it's circular, will be circular. If it's like a spider web, will be spider web. We do not impose any of these things.
Can I ask also a question? So you're talking about structure that are inside the entire cloud, right? That are spread, but really close to the cloud where the cluster already formed. Like how they are.
I mean, this is the cluster. This is the spider web that you have here. The problem of this cluster in particular is that we are already late. We are late to understand the origin of the trapezium cluster, but the Hacar region it's here is, I mean, the entry space is actually not the best one because you see that you lose it here, but it's also in one of these junctions of this.
Yeah. So basically, my question was more related to, I understand this is a good representation of the structure of the cloud, but system that already somehow formed the massive stars. So it would be very interesting to do the same kind of analysis on a primordial cloud.
Yeah. So the thing is that we need to do, yeah. So we need to be or to try this in younger quotes things. So the even earlier stages of this. The thing is that the structure is there. So but it's true that we will be better have it and actually on the glass. For example, like Pareto, this one. So this is one of these objects, and I mean the structure is already there, right? So
Even there, already, that objects already have an evolved process side. I really would like to see, I mean, I believe that in terms of structure of the cloud itself is, there are those multiple substructure. What I wonder is, what is the role of this multiple substructure in forming then the
no, I completely agree. We would like to have an even younger targets. Yes, I completely agree. We provide you the targets.
So here, this is the total mass you get not integrating the mass that you see in Arnold from the single dish. Where this mass and top, where that's
No, this is the total dense gas mass that we detect in our armaments.
oh in the ARMA.
Because this is what we can compare with the number of structures that we identify. Of course, if you go to the single dish, you have much more mass. The larger you go.
Yeah, but I mean those things have to come from the larger structure. That's the idea. So perhaps trying to correlate that kind of metric with the larger scale.
Next slide.
Okay.
Yes. Great that I motivate these questions to you. That's exactly the point. Yeah. Yeah. Because so the problem here is that we should not talk about individual fibers, filaments, or structures. This is a common mistake we have been doing for the last 100 years. That people have their own filaments and then say, well, this is my filament, this is my mass, this is my size. That's it. No. This is something that we learned for the latest protostarran planets, where we had the task to review the state of the art of filaments. And what we did was something really simple. We decided to be democratic with everybody. Everybody's right. And then we plot everything that people call a filament in a single plot, just comparing two simple properties, mass and length. That's it. What you'll find here is that filaments extend, what people call filament, extend over 8 orders of magnitude in mass. So from a fraction of a solar mass to, I mean, 1 million, and from scales of over 5, like these tiny little things, up to 100. I mean, maybe somebody would like to put something here, right? Juan? I mean, these are atomic filaments, so they are different. Let's see what happens. A little bit of molecular filaments, they extend all over the place here. And actually, a big contribution, thanks to Eugenio, came from the Hacar catalog, actually, most of them, because they cover this wide range in mass and sizes. The thing here is that structures, filaments are not unique structures, are not one-scale structures. They are hierarchical. You saw before that we have these filaments within filaments, right? Depending on whether you consider the large-scale Hertz filament or fibers, you are in a different position here. But basically, your structure is a hierarchy of structures. Interesting thing is that fibers are at the bottom of this cascade of structures. And as I showed you before, this is where there's no turbulence anymore. And this is where you fragment and form stars. But, I mean, filaments extend all over the place in this case. And a nicely correlated trend in this mass length phase space. Pay attention to something that I will explain later. These are filaments. High mass stars, HAPS, that I mentioned before, are of this trend. And that's the key to understand how they form. So let's go first for this. Because they are hierarchical and scale-free structures, it's more convenient to basically forget about identifying one or this or that filament. It's more convenient to talk about the scaling relationships, how these things connect across scales. So not, as you said, not just look at one specific thing. This needs to be connected to the last scale. And then, and we explain this, they follow different scaling relationships. So the most important one for us is the length-mass relation. So this scaling that you see here is basically what goes across all these scales. But that's not the only thing. So you have a scaling relation for the velocity dispersion of the gas inside these objects that also scales with length. So longer objects have more turbulent motion. So the higher filaments are probably way more turbulent, or they are way more turbulent than over fibers, right? There is a density-length relationship. So this is part of the intrinsic definition of the hierarchy. So large-scale structures that break into smaller and smaller and smaller and smaller is because the density gets denser and denser and denser and denser. So the density structure basically is connected to the scaling relation of this. And last but not least, this implies a full maximum length relationship. So the width of this object will change with scale. This is not the first time people have said something like this. The hierarchical structure of the ISM is a really old topic for discussion. And for that, you have what is called the Larson relationship to define this scaling. There is one difference here, and this is the most interesting part. But now, instead of the three, so 1 to 3 Larson relationships, we allow an extra variation depending on the aspect ratio. So you can vary independently length and radius of these objects. That's the update, so to say, to the Larson relationship that are basically almost identical to the first three that we have. So length and width can change. And this is important. So how do we understand this correlation? Well, let me show you in a few cartoons how this can be. So how do you move in this parameter space with the filament? So just take a standard filament, length, will have maximum and mass. These are the typical properties that you can define. And there are different processes that can change this mass, length, and full and maximum properties of the filament. I will summarize this in 3 physical processes that can happen. So you can have, for instance, accretion. You can interact with your environment, you can gain mass, right? In a simplified way from the sides. So you gain mass inside, and you can do it with a typical time scale that we can define this. The time scale that you need to double your mass. This is a time scale that you can define for this. There's another process that can change these properties and that actually generate the hierarchy. Is fragmentation. You can basically break your structure in different structures, and then you change the mass and length. You have here the formula. Basically, it's a kind of a threefold type of time scale. But basically, you can break it. And what I mean breaking is not just creating cores. You can fragment it in many ways. You can fragment it, you can cut it in half. You can fragment it in random pieces, right? And this is important for later. And the third time scale is that you can, as a whole, the whole thing, assuming that you cannot collapse much after, the whole thing can also collapse longitudinally. This last time scale is usually disregarded for good reasons. It's because this is it's a version of the threefold time, but modulated by the aspect ratio. So if you have a filament that is much longer than the width, I mean, typically the way we define filaments, you can basically ignore this part because these two processes will be much faster than, so it doesn't really matter what happens. Yet. So in filamentary geometries, the only thing that you need to take care is this accretion timescale versus the fragmentation time. How fast you accrete mass compared to how much you fragment, and how fast you fragment. And this is because it defines actually a really nice position in this mass length phase space. So if you have fragmentation, what you do is basically your large scale hierarchy breaks into several, two at least, structures. So your mass is lower and your length is lower. But why, in which way is lower? So if you will, you have a stick here, but if you have a cylinder and then you chop it in half, you have two fragments that have half of the mass and half of the length. So if that will be the way you fragment, the slope that you create here is basically 1, because the mass per unit length, the mass per length is preserved in this chopping, so to say, fragmentation. What we see is a fragmentation that goes with half of the, so 1/0.5 in terms of mass. And this fits nicely with what is called turbulent fragmentation that can be basically modeled in terms of random walk. So in terms of just chopping in half, you have a fragmentation that can overlap and things can have different lengths and different structures and different masses. And statistically speaking, this follows this m/1/2 scale. So fragmentation competes against accretion. Accretion basically just increases your mass. And it wants to move a point here into that direction, just gain mass. Until these two timescales compare. So when these two things are on the same order, then you fragment and accrete and fragment and accrete and fragment and accrete and fragment and accrete and fragment and accrete. These two things basically set your slope, and then you go to the next level, and this is how you keep your m/1/2 relationship. So filament that fragment and accrete will follow this L proportional to m/1/2. And it will be basically bracketed between these two things. The fragmentation from the higher scale and the accretion rate on the lower end. Going back to the plot, this is the way we bracket our filaments here. We have, if you start from one of the structures, and then for instance, the ISF, the one that you showed before, is here. You cannot go above here because this is your fragmentation, and then you accrete to the point that you have your fibers here. This is how you bracket your filaments. And the typical accretion rates in the galaxy bracket the entire distribution. These are your filaments, filament fragmenting. The standard thing that we see here is basically filament fragmentation. But what we are interested in is what happens with high mass. So why the hubs are off this trend? Hubs do not form by fragmentation. You cannot form a hub by pure fragmentation. You do not have a filament massive enough to fragment, massive enough and stable enough to fragment to form a hub. You need something else. And actually, this is the last thing that I want to show. This is a project that we started with Eugenio. So this is the Protestant and Planets review. We did now a new study that is under review that we now focus on. This is the filament before. Now we focus on hubs. We took what people call hubs, again, no distinction, but when they could give us mass and length of these hubs, and look at what they are. All of them systematically pop up there. They are off the main filament thread. Interestingly, you can compare what is called the threshold for high mass hub formation. So there are already surveys. Alessio, for instance, is working on that. So there are thresholds on galactic surveys where you see a mass radius, in this case, correlation, where you form your high mass. And then defines a line here, assuming that you can convert the radius into a length. So there's some trick here. But this is the threshold that should cross, and then your hubs are there. So your hubs are the actual precursors of your high mass stars. So why are there and how they form? Well, that's a really interesting thing because, and you cannot, I couldn't believe how simple is this. If you take the scaling relations that I showed you before and you assume some cylindrical geometry, you can prove that your scaling, basically, because the L is proportional to m/1/2, but you can also define as a 0 point of this thing. And you can prove that A depends on the aspect ratio. So you have different positions in this plot depending on your aspect ratio. That's interesting, right? So hubs are more roundish, so they should be in this part that things are more spherical. So you have really elongated filaments, slightly less elongated filaments. Filament, basically, people define filament something that is above aspect ratio of 3, and hubs are below that. So at least in this simple approach, this is the way, or they lie on the place that they should. Things that are not filaments anymore, things that are more spherical. Spherical at scales of 1 parsec and with 1,000 solar masses, but spherical, after all, if you consider the entire system. So what changes then? I mean, fine, but go back to this thing. What I said is that in filaments, you can't ignore the longitudinal collapse because the aspect ratio is too long. But this is not the case anymore. Your aspect ratio now is important. If you change to this symmetry of geometry, so basically you change to something more spherical, less aspect ratio, in general spheroidal, this time scale is equally important as the other two. And then you create a different process. So what happens is what we call a phase transition. So it's exactly the same process as before, but nothing changes. So the physics is always there. It's only that when you change to this arrangement, the more spherical thing, what you generate is a global collapse. So it's not that you have these two things fragmenting and stuff that are still happening. So the hubs still interact with the environment, still fragment and form little pieces, but the whole thing is now collapsing. The physics is the same. There's no new physics there. It's just that time scale matter in this geometry.
So, Alvaro, if I may ask, the collapse that you see in all your filaments is basically turbulent collapse because it's this random work that gives you this
Fragmentation, not collapse.
fragmentation. Yes, but yes, the fragmentation is turbulent here. Unless you go in the hub filament system, which the fragmentation is gravitationally linear, basically, because it's
No,
the
no, no, no,
linear
so-
one.
This is what I'm saying. These three things are independent and happen at the same time. So you have fragmentation. So you don't have a homogeneous thing. You have something that is breaking into little pieces. But at the same time, the whole system, and this is why it's important to look at the system, not at the individual pieces. The whole system is collapsing because of the geometry. It's a geometrical phase transition.
That collapse is gravity.
Yeah, this is gravity.
Yeah,
This is gravity.
that is gravity.
This is gravity, but it's the
It's not
system.
in the filament, but the HFS system. That's what you are saying. No?
So the whole system is collapsing now. So gravitationally collapsing. So the longitudinal collapse is gravitational collapse.
Yes, which is dominant only in this hub system, basically.
It's dominant when you have a small aspect ratio.
Yes.
And I mean, dominant. It's on the same importance as the
Yeah,
other
but
two
at
processes.
least, yeah.
So you are collapsing at large scales while fragmenting and accreting. So the three things are together. So then now we can explain why things are in different places. So when you have one of these filaments, Herschel, Hacar, low mass, high mass, you are dominated by this accretion versus fragmentation process. And then you will move along this line. This is why most of our filaments follow this mass length relationship. But then you have a hub. A hub is basically a region, and I will not enter in how you form it, but just assume that you have them. Where you have intersection of different structures and filaments together. So individually, none of these filaments can form a massive region, but if you put them together, all of a sudden, you generate a really high mass region in a compact area. So you move from these individual things down here. So more massive, smaller here. And then you trigger your collapse by pure geometry effects. Then your system basically collapses down into this. And this is how you separate your hubs from the filaments in the general picture of the ISM. What happens here is what we call an emergent phenomenon. So it's not that there's a new physics. It's not that you need to invoke a different process. It's that when you put these things together, when your density grows enough, in this case, and you create this overall more spheroidal phase, you basically trigger this process. Before it was there, but it was too slow. So this is why you do not form high mass stars in these things. You will never be able to do it here. You need this phase transition. And with this is what you start forming your high mass star. You basically, you already are prone to collapse. You are prone to form your high mass star at the center. And at the same time, you keep accreting. And at the same time, you keep fragmenting. And at the same time, you keep forming your low mass stars. This is how these two things go together. This is how you form high mass stars and low mass stars together, because you keep forming them regardless. This is the same process here. And you need this phase transition to occur.
I think I have a chicken and egg problem here.
Yeah.
I mean, you make it sound like the fact that you have these filaments, but these filaments happen to be in this morphology, they are driving an overall collapse because of their morphology. All it is because there is something that is forming in special condition that is in structure in this system. So this is just the result of another phenomenon.
How you end up in this situation is true that we cannot say. The large scale filaments are not collapsing to the center. These guys here is not collapsing here because at these scales, this elongated geometry is fragmenting faster than collapsing. It's only collapsing this central part. So there's no global collapse as a whole, unless you put so many filaments that the whole system becomes again spherical or spheroidal, and then you collapse. But the only thing that is collapsing is the center. But it's true that we cannot tell from our data how you end up in this situation. That's absolutely true. What triggers this configuration? That's absolutely true. But once you have it, it's just simple timescale problem.
The two observationally see the collapse in this.
We see there are many examples of local faster scale collapse of big hubs. So I mean, the previous Pareto's paper in 2013, we also saw in the nebula cluster, you see an accelerated collapse of the regions of gravitational collapse. So this is relatively common to see. I mean, people already, I think, kind of agree on this collapse. But the question is how you trigger this collapse. And the triggering is just a timescale problem. It's just the way you change the geometry, then this collapse becomes important. It's always there. Again, this thing is trying to collapse, but this collapse is so slow that you will fragment and form your stars much earlier. So that can happen.
So you're not a fan of the conveyor belt things along filaments?
It will happen in this field. Again,
Only there.
the thing is that so I'm against the idea of everything at all scales doing it. But inside here it will definitely happen. So and again we have the I don't want to go back to that.
The size of the other plants.
Yeah, but the key point is the N over M. No, you can have let's say the L over M ratio at any scales. That depends on the density of your region. You can have it at 1 parsec, at 1 parsec, at 10 parsec in some extreme.
You will be moving here. Just
So in this sense, I would buy the idea that it's not global collapse, but it must not be a 1 parsec scale. That depends, to me at least, on the density of the regions. At super dense regions, you can have this blob up to 5 parsec, for example. Exactly.
so the thing is that you need to enter.
Most extreme one are 2, 3 parsec. In this case.
So I didn't have the time to explain this, but the thing is that you need to enter a specific area in this mass length phase space. So this is the virial relationship. So that we have for filaments. So if you are around this area or above, you are subvirial. So your motions will basically keep your structure there without doing it. So first you need to enter this supervirial region. And then the second thing that you need to do is to become spheroidal. So if anything, there's something that we discussed in the paper that we will not discuss here. Technically speaking, what we are saying is true for anything that happens here.
Yeah.
It's a scale-free process in this sense. It's just a geometrical thing. If you are here, you can be here, here, here. Everything would experience the same process.
To me, my point is that I don't think that we are there because there is something else that is cutting out to the fact that we don't have like 1,095 solar masses in a half. This is never been observed.
Not now. Not now, but in our
gas, there is no abscess that is so massive. So for me, there is something that is cutting off the amount of mass that we have
now, again, we do not have anything in our galaxy that fulfills this criteria. 100% agree. Globular clusters should form somewhere. And the idea is that all of these, so all these relationships depend on the scaling relationship that we have. If you manage to change them because of the initial conditions, high redshift conditions, you will see these things and you will have different relationships. Anyway, my point is that, going back to the laser comment, this reasoning that we are doing is a scale-free thing. And it happens
Problem. With all these questions we are doing.
Well, it's great. It's great.
Yeah.
Yeah, I'm just finishing. So the last, that was actually my last slide. And just to leave you here with the conclusion that, I mean, there are different levels of the discussion if you want. I hope I convince you that having the resolution and identifying the substructure is crucial. And actually, things do not look so different anymore when you have these maps with Alba now. We think that these fibers are the nice bottom of this cascade. This is what you need to form low mass stars. And then when you put them together, and depending on the conditions how you put them, how you arrange these networks, and the network reaches some kind of criticality, then you produce this phase transition, which is basically what triggers your high mass star formation. I agree that this is the point for discussion. Actually, it's a paper that is not yet out, but I hope we can discuss it either over lunch or, I mean, in the coming months. So thank you very much. That was just the last one.
So I think we had a lot of questions, but I'm going to ask it. Sorry, we are going over the hour. So if there is any other small question, I will take for 1 or 2 questions, even from people from online.
Maybe just to remind, because I think it's also interesting the discussion later at 2:30, we can also discuss about how you get into these images if somebody's interested with data combination and stuff. So just to,
yeah, there will be another talk at 2:30.
So you got that cheap speaker. You get 2 talks for the price of 1.
Yeah, on the data, basic building up the data.
It's more technical. This is what we do.
Sorry.
So am I right to think that now the problem is determine what sets the aspect ratio? And do you have an idea of what physics is that?
A statistic.
About fields, right?
Of course.
Well, so the thing is that go back to the. I don't know how, I mean, we have thanks to Eugenia, we have statistics to do a lot of things, and this is the toy model that we have, right? That correlates the aspect ratio with the position in this plot. It also correlates the column density. So what you have is that low column density filaments are long aspect ratios, and high column density filaments are small aspect ratios. This is what we can test, and we already did in the paper. We test that, and this is already happened. So we have statistically this done. What we need to do is also to actually measure the aspect ratio statistically, because this is what the Hacar survey, I think, is limited in the sense that, I mean, we don't, correct me if I'm wrong, the real profile is not as nicely measured in this way. So we need to do this here. But we have already hints from the statistics that we are not too far off, and atomic filaments, long aspect ratios, low column density.
If I can add just because Alvaro contacted me when he already had this work in progress, and when he contacted me, he was asking me if we could measure somehow from axial filament the aspect ratio with precision. So he asked me for measurement of the full width of maximum of the filament. So we have an estimate of the length. We can agree or not agree that there is some uncertainty. How much we could compare with the aspect ratio, and unfortunately, I did this measurement, and the point is that the full width of maximum of the axial filaments at axial resolution, the column density matrix was much broader. It was hard to constrain the full width of maximum, also because the structure are not really very linear. They are very.
I mean, they go in. To be honest, they go in the right direction. The point that we cannot say
it's
it for sure, but they go into the right direction. And for instance, just to put some examples, so Musca, really long aspect ratio. So it's on the order of, I think, 20 parsecs or so. No, sorry, something like this, and several parsecs long. So in this area, our fibers, really dense, high column density, short, low mass, low aspect ratio are here. Hubs are here. The ISF is somewhere in between. Nested is up there. So we have kind of good hints on that. But it's true that we need to quantify the width in high precision to do that. Yes.
I sorry, the point what I was saying is that, yes, there was some indication that higher aspect ratio was there and lower aspect ratio on there was lower, but our data, at least the 500 micron resolution data was not so strict that we can disentangle it so well.
They go in the right.
But they go, no, the trend is there, but it's very, very.
I think my question is more general, more naive. I was thinking of, if you imagine the galaxy, and it's a multi-phase system, and then you check what sets the aspect ratio of this phase, and you can like describe what its probability distribution of aspect ratios.
Yeah.
This is, you can actually see if that matches to the population.
Well,
that you have in each.
Yeah, so the connection between these geometrical properties to the physical origin is important. Is I think what you mean, how
Exactly.
what sets that, right? So one thing that that we can say is that so aspect ratio changes this, but also the correlation between the fragmentation and the accretion. So the accretion is the other parameter that sets here. So when you move down here in small aspect ratios, because you have higher accretion rates, and that should be a process that enables that. So if you have something that, for instance, feels perpendicular to them, it will be harder to accrete and others. But we cannot say what initiates and triggers this first reaction. The same way as we cannot say what put these guys here in the first place, right? The idea is that we need to go back again to not just defining one of these things. We need to investigate the full hierarchy together.
Last question, because we are very.
We can continue, Balance.
But we can.
Very quickly, but I mean, when I was doing this analysis of development collapse in the clouds, so aspect ratio 1 basically, I was looking at the surface density as something that would drive this kind of development collapse, which is more or less, I guess, the line that is there for the upsilon system. Now, my question is, since these things should be at this point hierarchical, those are partial upsilon systems, but you have also something very down, like here. I mean, those objects, do you look, these are kind of up-filamentary system at the other scale? Yeah, the fibers going through some kind of one. I mean, it would be very nice, I think, to count, I mean, to quantify if there is similar kind of up-filamentary.
So again, I should
fiber system.
please invite my student. So when you do the statistics of these guys, so you can say, so you the first measure them, you know all the mass and length, you know which ones are forming stars.
Yeah.
They are here, and there are those that are. So, because the process is.
So even the up-filament system is hierarchical in a way. It becomes fiber system.
Yeah, so people call them instead of, so the hub filament is typically called, so these guys are.
Scale.
Oh, sorry, exactly. Those are the other, the big ones, but people call them forks and stuff like this. And the forks and things are here. So the typical size of a core, typical size of a future.
And the density scales in this way.
The density scales here.
Yes.
So the average density of the system. So the average density of a dense core is the same as the average density average of much larger scale of one of these guys.
So the scalar is not only by the ratio, but also density. You mean, you
The-
bring up, not down.
So yeah, so the different, because you have all these connections in the scales. So sorry. So you move here aspect ratios column density, but you have the correlation also between length and density. So if you move smaller in length, you also increase density. But the thing is that we think about in terms of the whole hierarchy structure. So you have but in length and scaling in density. So up density, down length.
Can we discuss? I think we can here the discussion
Yeah.
and.
Gracias.